Okay, wonderful. So let's get cracking. I'm basically going to talk the next 15 minutes proving Rick's last point on his slide, saying that mineralogy is important and the beneficiation of rare earths is complex. But as a short introduction, and I just need to make sure I can actually move this. There we go. As a short introduction, as Rick has already mentioned, rare earths have quite significant economic and strategic importance going forward for a lot of high-tech industries. Industries like the modern defense systems, a lot of electronic applications, and the drive for green technologies. Now, rare earths are basically comprised of the 15 elements that make up the lanthanoid series, plus yttrium and sometimes scandium on the periodic table. And they're also subdivided into either light rare earths or heavy rare earths. What is interesting to note in minerals processing, we try and separate or beneficiate minerals. Rare earths is present in, can be found in more than 250 minerals. Some of these minerals can be either complex or selective, so either containing all of the rare earth elements or either predominantly the light or heavy rare earths. They also can range from being silicates, oxides, carbonates, phosphates, and halides, and they usually occur in low concentrations. So you can already start seeing a picture of how complex it could potentially be trying to separate some of these minerals. So just for a note, when I refer to mineral beneficiation, what I will be referring to mainly is any physical processes that we employ to improve the economic value of the ore. So it's usually a primary stage of processing, primarily with the aim to reduce volume that you then have to process in further hydrometallurgical or pyrometallurgical operations. It has a very important aim of removing a lot of your gangue minerals as well as harmful impurities, and then to produce a concentrate of such a grade and composition that it's suitable for further processing. When we think about beneficiation, it usually consists of two main steps, and we will explore that in a bit more detail later on. It's liberation and separation. So to provide a quick glance at rare earth mineral deposits, currently you'll see on the, let me see if I can get a laser pointer going. So this map I obtained from one of the AusIMM bulletins. Basically provides all the significant projects that's in production, or where some of the green ones where resources have been identified. These deposits are broadly classified into 4 geological domains. So either your carbonatite deposits, alkaline or per alkaline igneous rocks, placer deposits, which is basically mineral sands, and then iron adsorption clays. Now the carbonatite deposits, probably the best example would be the Bayan Obo and Mountain Pass mines, Bayan Obo in China, Mountain Pass in USA, as well as Mount Weld in Australia. They're usually larger, higher grade deposits and a good source of the light rare earths. And one of the common minerals, rare earth minerals found in these deposits is bastnasite or monazite. Now, the per alkaline deposits, this is probably where a lot of the future opportunities exist. They are a lot more complex and highly variable in their mineralogy, even within the same deposit, but also among different deposits. They have a flatter distribution of rare earth elements usually, which means that they can be a very significant economic resource for high rare earths. A good example is the Kola Peninsula in Russia that's currently in production. The main minerals in these deposits is usually lepidolite and udilite. I think that will probably do for that. So moving on, this slide basically gives an outline of, as an introduction of the different processing strategies that you can use to beneficiate the different types of deposits. So carbonatite deposits are predominantly beneficiated using flotation, but a lot of gravity separation is also employed, magnetic separation as well. Your alkaline per alkaline deposits, again, predominantly beneficiated using flotation, but again, also gravity and magnetic separation. Your mineral sands deposit is usually beneficiated using gravity separation, or also a range of flotation, magnetic separation, or electrostatic separation. The only odd deposit is the ion absorption clays, where the rare earths aren't actually contained in minerals, but they're absorbed onto the surfaces of clays. And these deposits are predominantly located in China. And the main method of beneficiation is ion exchange, usually using dilute solutions of ammonium sulfate. Now, the reason I've put this up is already just to paint the picture of how complex it can become to beneficiate these deposits, and also to highlight that even though the processing could be complex, we do have a range of techniques and processes available for us to employ dependent on the characteristics of the ore body. So, for instance, gravity separation is really suited for material to separate minerals with a high difference in their specific gravities. And they're also more usable for in size ranges of about 2 millimeters down to about 75 microns. Magnetic separation uses the difference in magnetic properties of materials. And I mean, a good example of how it's employed currently is in iron ore operations, where magnetite separation is very well established using wet, either wet magnetic drum separators. Flotation, it's probably the workhorse of the minerals processing industry. And there's a lot of knowledge available on froth flotation of both sulfide and oxide deposits. And as we'll see later, probably not so much on rare earths. So we've already identified that there's multiple separation options that we can employ to beneficiate rare earth deposits. These processes can also be combined into quite complex flow sheets. As I've mentioned, in some deposits, you can have a multitude of minerals present that contain rare earths, and you therefore need to employ a sequential processing strategy to upgrade the ore into a usable concentrate. The beneficiation route is highly dependent on ore mineralogy. Then I've lost my pointer. As you can see on the side here, this is just an example of the Bayan-Obo flow sheet that's available in literature, where multiple stages of magnetic separation as well as flotation is actually used to produce a rare earth oxide concentrate that exceeds about 60%. So this proves the first point that Rick also made, is know the ore. To really understand how to beneficiate any rare earth deposit, we will need to understand the resource early, its composition, its mineralogy, texture, as well as metallurgical characterization. This will be key so that we can evaluate the different beneficiation techniques and identify the most suitable processing route. And by doing this, we would have the ability to develop an optimal flow sheet. So knowing the ore unlocks value. So I mentioned already that beneficiation consists of two processes, mainly liberation and then separation. So it's important to note that in minerals processing, we typically talk about the recovery of the metal of interest, for instance, copper or gold. But in practice, when we perform mineral separation, we do not recover the elements. We actually recover individual particles, and these particles will contain different mineral phases, of which the mineral phases contain the valuable elements we're looking for. So a key step of beneficiation is to reduce the size, or using comminution to break up large rocks, so we can actually create particles with the discrete mineral phases that we can then recover in a separation process. So we know from experience that usually grinding finer tends to improve liberation. And again, liberation is a function of ore properties like hardness, texture, and your mineral associations. If we improve liberation, it allows us to reject barren particles and improve separation. So as an example here, this is for a chalcopyrite ore with a 200 micron scale. You can see chalcopyrite disseminated within the particles. So when you do recover these particles, you will also be recovering quite a lot of gangue material you're not interested in. When that same ore is crushed down to 100 microns, you start liberating material where you can then recover it without recovering a lot of gangue material. So that's the first step, liberation, and then separation after that. So one of the common separation techniques we use is froth flotation, and it's also widely employed in REE beneficiation. So froth flotation is a primary stage. It's a physical chemical process that we use to separate valuable minerals from unwanted minerals, and it is an incredibly complex process. Both chemistry and hydrodynamics are interlinked, and even after 100 years, feels like 100 years, it's still not fully understood. Also, your flotation performance is very much system specific, which means that you do need to do quite a bit of test work before you can optimize for a specific deposit. So how does it work? On the left, I'll grab my pointer again. On the left is a cross-section of a typical flotation cell where you induce air through a shaft. You have a rotating impeller that then suspends your slurry. And when you introduce the air through the impeller, it generates bubbles. Your desired particles, which is shown in red, hopefully preferentially or selectively attached to the bubbles, and are transported to the top of the cell into a froth that is then recovered into concentrate. Hopefully most of your unwanted particles leave the cell via the tailings. Now we spend a lot of energy on grinding rocks, and one of the reasons we do this is flotation operates in a very narrow size range, usually between 10 and 150 microns. Outside of these size ranges, efficiency drops quite dramatically. So comminution is again a vital step as a conditioning step for flotation. And we adjust the flotation performance using chemistry, usually by carefully adjusting the reagent suite we use. And this is again specific to the mineralogy of the deposit. So I've mentioned that froth flotation is widely applied to the beneficiation of rare earth deposits. And that's mainly because of this ability to process a wide range of finer particle sizes, but also because it can be tailored to the mineralogy of the deposit. Now, unfortunately, unlike sulfide flotation or oxide flotation, our knowledge base for rare earth flotation is pretty limited, with most of the work being done on the flotation of bastnasite and monazite, and limited information on a lot of the other rare earth elements. Having said that, though, there's also an additional opportunity, which I've sort of been speaking about beneficiation, but there's also this potential for pre-concentration, where there's a significant opportunity that if we can reject coarse unwanted particles early in the system or in the process, we can reduce the amount of energy we consume to grind material fine, to liberate them, to be able to separate them. But it also means that if we can reject that material, we don't have to process it, and we can improve throughput through our processing facilities. Now, at the JKMRC, we are currently pursuing research programs targeting two potential technologies, one being coarse particle flotation, using a teeter bed flotation device, which is basically a fluidized bed. And this is capable of potentially floating particles up to 1 millimeter in size, as well as using high voltage pulse comminution coupled with screening to reject barren particles very early on in the process. So I think the aim here, or the message would be that if we are going to pursue the beneficiation of rare earth deposits, we need to be cognizant that a lot of the existing work has focused on the Bayan Obo and Mountain Pass deposits, and we don't necessarily have the requisite background information on some of the research that has been done, and we don't have a peer-reviewed knowledge base for newly identified deposits. This presents us with a significant opportunity for future research to support the design of beneficiation processes targeted for rare earth minerals. We've already seen, like I've mentioned, rare earth beneficiation combines multiple steps of different separation strategies to produce your final concentrate, which can then be further processed. And one of the most important techniques we still have available for use is froth flotation. But if we are going to do this, developing the beneficiation processes for rare earths, we are going to have to tailor that to the deposit characteristics. And that is it for me. Thanks. I hope I kept to time, Rick. I'm not sure if I've lost everyone there.
I can hear you, Lizette.
Okay.
Sorry, I was talking into a microphone that wasn't working.
Okay.
I could hear you. I was saying I hope you could hear that applause. No, I don't think you went over time because you started late because I went over time. But I thought, so we don't have a lot of time, but if anyone has a burning question, we can deal with it. And if not, we might, question online.
Lizette, have you looked into rare earth beneficiation strategies for phosphorite rare earth deposits, or are you aware of any studies looking into mineral processing of these rocks? That's from Diana Zivak online.
Okay, so I'll answer that, I think, live. There was a very interesting review paper on different strategies for beneficiation of rare earths that was actually published this year. In that, it does cover phosphorite deposits, but again, it's plagued with the fact that we do not have a substantial database of knowledge of the different flotation strategies to use for these types of deposits. So there has been some small scale tests done trying to identify suitable reagents for use, for instance. But so far, nothing that I currently know of that's been successfully implemented in the sense that you produce very high concentrate grades. Now, I should probably, if I can share again.
Oh, actually, we probably might, we are a little bit over now, so.
Yep. So I might just say that if you're interested in finding out more, at the back of the presentation I just gave, there is a list of references that actually reference this review article. So if you're interested, we can always touch base later on and I can provide you the reference and you can have another look at what is currently available.
Yeah, and we'll be putting up the presentations too for the ones we can anyway. So thanks very much, Lizette. That was great.